Okay, in the last couple of videos, we explained what we're going to do and how we're going to do it, and we showed you how we did it. A lot of that may not seem very clear because some of this stuff with symmetry and symmetry breaking, I can't really explain the level of detail that I would like to. It's just actually a little bit too difficult for most people who aren't freaks to understand. But now we can understand what we've got. We've got a data table. We've got two different data tables. All they are is mathematical graphs. They are filters through which we can analyze the data. Okay, if you're going to analyze data and you're going to use a mathematical filter to do it, the first thing you want to do is get a mathematically correct filter. This goes without saying. This filter is incorrect. This filter is mathematically correct. Now, once we have the table and we put the data into it, then we can do other stuff with it. Okay, we're not just limited to putting molecule names in. Now, the molecule names aren't data, it's metadata. The name you gave the molecule is beyond the data, it's metadata. Okay, we could have named the molecules 1 to 4 and A to whatever, however many letters is 20. Anyway, we didn't. We gave them these hokey ass names. Well, instead of using nonsense names to name your variables and using your values to name your variables, why not logically name your variables and then let the logical names name your molecules? So in my case, I started with colors, so I kept the colors. And then I use those colors as more metadata. So in other words, there's so many properties of these molecules that we could graph. How do you pick one? Well, the most important one, in my opinion, is water affinity. So I picked water affinity as my metadata. I use colors to do that. So I said blue loves water because the ocean is blue, and that's my favorite color. Red hates water. It's angry. It hates water. So if you use a color wheel, then you go from blue to green to yellow to red. You create a rainbow. Okay? So we can have a spectrum of water affinity. We can assign those properties of water affinity to the molecules by assigning them colors. So then I use the colors that we used to do the nucleotides, and then we assign, I assigned A to blue, C to green, G to yellow, and U to red. I like U better than T because it's artistically better. I don't like that T, I like the U. So that's how I picked it. I could have done T, I could have done U. U looks better, so I use U. So it's an mRNA table, okay? In retrospect, I probably should have done T, but I like U. So anyway, we stick this data into our table and we use this metadata. Now we can analyze it. Okay, we could say certain things about it. The first thing that we notice about this code is it's perfectly symmetrical. This is the most symmetrical code you will ever see in your life. Okay, the next thing we can say is it's highly optimized. We've taken an object, we've compacted this information. Okay, these are things we can say about the table, but they're also things that are true about the code itself. So it's objective, it's perfectly symmetrical, it's highly optimized, and it's nonlinear. Okay, so which means that there's no one-to-one. There's many dimensions of information. Each variable could contain many dimensions. The basis of the information itself is spatial. Okay, they eliminated space. They said no space, one-dimensional space. That's impossible to believe. And they go on and they say that sequence determines structure. That's logically incoherent. What the hell are you saying? You're saying something. You're saying false is true. I mean, that's just stupid. Okay. Structure determines sequence. So we start with a structure and we can derive a sequence from it. That's always true. All molecular sequences are at first structures. Okay. Stop saying that. Stop saying there's no spatial information. Stop saying it's sequence only. These are false things. Stop saying it's simple. Stop saying it's linear. It's complex. Okay, just stop. Now, this table is the coolest damn thing you'll ever see. But the other thing you need to realize is this is not a static. This data, this code is not static. This thing, you got to animate the table. Okay, and the way you do that is you think in terms of probability. So that's better. Okay. So instead of saying that this codon means this amino acid, you need to start saying there's a probability of a codon, and it's associated with the probability, because there are all of these crazy ass molecular behaviors. You've got to transcribe it, and then you've got to translate it, and then it's got to follow. All of these different behaviors are probable. There's a probability that they will occur. They must occur for this probability to be true. So it's not dictating that these things will happen, it's predicting it. So this is not like a Lego system where we have things that we plug in. This is a crystal ball. Okay, this is a matrix of probabilities. This is probably proline. This is probably cytosine. This is probably leucine. Okay, probable in what context? In a specific context. So you take all of the possible codons and then you reduce it to one. It's just like a photon collapsing to a specific place. There's all these. Okay, this is literally what life is doing. It's like an artificial intelligence. Okay, it's the question is which codon. The answer is this specific codon. It's created this probability matrix of what might be a codon. All you have to do is say, look, any 3 nucleotides on one of these strands has a probability of being a codon. Well, right out of the gate, the probability is 50-50 because there's 2 strands. Okay, that probability is going to change based on what reading frame you use. So there's not only a probability of being a codon, but there's also a probability that the codon will change. So this symmetry breaking that life has done is based on those probabilities. So it wants to put the amino acids that it wants to be most sure of in the highest probability states. So the 2 amino acids it wants to be most sure of are glycine and proline. So it uses the most powerful codons to achieve that goal. So that if it's glycine and proline, then what's going to happen is the protein's going to turn. Doesn't matter whether it's glycine proline or proline glycine. So this is a grammar. There is a protein grammar, and it's embedded in the probability of these assignments. Okay, so what it wants to say is, well, if I make a protein and it turns at this point, if I alter this gene in any way, I want to keep the high probability of that turn. So that's symmetry. It's using the symmetry of the code to maintain a symmetry of grammar from one protein to the other. Well, this gets into the question of why it would do this, and the answer is because it's a search. Okay, this code, yes, it builds proteins, but building proteins is fairly easy because they're crystals. It's easy to build a crystal. What's hard to do is search. So these probabilities and these assignments are so symmetrical because the code, the language itself is symmetrical. So, we say 1 gene, 1 protein, that's ridiculous. We don't even know. We pull out a strand of this, then it goes to a strand of this. We don't even know how that thing's going to be cut up and respliced together. We don't know what frame it's going to be. Okay, we don't know what this actual gene's going to turn out, and we sure as hell don't know what it's going to be over here because there's an infinite number of things that it could be. So it's collapsing to this codon, it's collapsing to this gene, it's collapsing to this protein. It's taking many, it's a many to many code. It's not a one to one code. You have to start looking at the code. It's a brain, okay? It's not a neuron. So you have to start looking at how complex this code is. It's fabulously complex. So it's creating, it's taking this set of highly improbable molecular behaviors, and it's learning how to make them highly probable. Okay, this is a crystal ball. This is a prediction algorithm. This is a probability matrix. This is not a simple linear one-to-one code, but you can see it in the data, and you can start to see these symmetry patterns that are everywhere. You can't avoid them. It's perfect symmetry, and it's based on the spatial symmetry that was broken. So we can say, you know, a codon is 3 contiguous planes of a dodecahedron. That's what a codon is. We can say that a tRNA codon is 4 contiguous planes of an icosahedron. And we can go even farther and say that the double helix is a sequence of dodecahedrons, and it's translated into a sequence of amino acids, which are tetrahedrons. So it's a differential geometry. We can even see the shape of the tRNA, which are ginormous, by taking these tRNA codons and slicing them to the center. It perfectly matches the shape of a tRNA codon. Because what the tRNA is doing is it's multiplying out. You know, you have a DNA crystal. It makes an mRNA crystal. You have a tRNA crystal. Okay, the protein forms on the surface of that tRNA crystal. Okay, it's controlling this unit of space through this unit of time in stepwise fashion. That's why it uses sequences. It is tightly controlling the implementation of this spatial information. Okay, this is not superstition. Life doesn't close its eyes and open and say, oh, look, a protein. Well, it could only be one protein. And that's just dumb. Okay, what it's doing is it's reducing the entropy of the 4 molecules in DNA and the 20 molecules in protein. And then it's reducing the entropy of these molecular behaviors so that it can create these new units of spatial information that we call proteins, because it's going to use them as the code becomes more complex. And as it does this, it's a fractal. Okay, at each level, it wants certainty. It needs precision. Okay, so it's reducing the sets that it uses so that it can increase the sets that it has available. So by the time you get to, I mean, if we look at this, all right, so the genetic code is a relationship between sets. It's a set of nucleotides, a set of amino acids. But there's all these other molecules, you know, the mRNA, those are sets too. Those are people too. Those are part of the code. Okay? This idiotic idea there's this idiotic idea called the central dogma, appropriately, because that's what all of this is. It's dogma. This is religious dogma. This is a cult. Okay? They say that molecular information is one-dimensional. DNA makes DNA, and DNA makes protein. So it's a fluid. It flows from DNA to DNA, and it flows from DNA to protein. But it never flows back in the other direction. It's a one-way valve. This is the same as electricity as a fluid. This is the same as heat as phlogiston, this fluid that flowed in and out. I mean, this is a common idea. They have this fluid on the brain where they say that information, okay, that's not what information is at all. Information's a field. Okay? DNA and protein make DNA. DNA and protein make protein. Okay? That's just how it works. It's a complex field. If anything, protein makes DNA. It's a kept molecule. It's like a beehive. It's like the queen bee. It meticulously gardens DNA molecules because it needs them for this code. So when you look at this thing, this is the genetic code. It's these relationships between these sets. The entire thing evolves in concert. This code becomes more powerful. It's inventing itself. So if you go back on early life, this code wasn't very powerful. If you come to contemporary life, this is a very powerful code. It's because it's been learning. This damn thing is highly intelligent. Okay? The code must evolve. It's evolving. It's actually inventing new math. Okay? And it does this by searching for the elements of the code that are better at being the code. And those elements in this table are the small set of nucleotides and the small set of amino acids. But we're going from 4 to 5 to 6 to 20. So see, the information is expanding. Okay, they're saying there's more information in a set of 4 than there is in a set of 20. That's just stupid. They're saying that the information gets compressed into the protein. No, the DNA molecule is the most highly compressed form of perfectly symmetrical spatial information in the universe. That's why life uses it. This is a mathematical fact. You can prove it with this damn machine. Okay? DNA is a highly compressed form of spatial information. There's an algorithm, a code, a system of molecular behaviors that decompresses DNA into protein. It does this in exactly the same way that artificial intelligence works, okay? It's not a linear process, it's a nonlinear process, okay? We need to start thinking in terms of complex nonlinear information because that's what the code is. But we don't even have to wonder about it because we can see it on the surface of this ball and we can emulate it with this machine, okay? It's not like we're confused. We know what we're doing. We're talking about a code. The code is animated, it's spatial, it's symmetrical, it's logical. It works. That code is what worked to generate this data table. Now, if you're trying to understand this with a mathematically incorrect, if you're teaching this to children, you're teaching them garbage. Okay, this is garbage. You're not going to confuse them. Just tell them this is a code. This is the most complex code you'll ever see. This is the most symmetrical code. It's highly optimized. This is the most intelligent thing on Earth. This is a high form of spatial intelligence. Now let's talk about these linear associations. GGG is associated with glycine. What does that mean? See how easy it is? You're not confusing the children. They can understand a code. They can't understand a recipe. They have cell phones, okay? They know that the file that creates the video image is smaller than the video. There's a decompression algorithm, okay? This code must make a protein from a DNA, but it also must make you from a single cell. It's the same code. All right, all it's doing is showing us its logical contours between DNA and protein. It's showing us the map, the logical mathematical graph, okay? That same code must take all the atoms on Earth on day one and organize them into life, okay? Took 5 billion years to do that. But there's a logical process by which it can be done. It's highly complex, all right? You're not going to explain that with this, okay? There's no way this is going to make life happen on Earth, okay? You got to see it as a mineral. It's a natural logical process. It's a crystal. Life is one crystal, okay? You're a part of that crystal. I'm a part of that crystal, okay? My cat's a part of that crystal. We're all sharing the same code. It's so symmetrical that it can create, life out of nothing, and it can create you out of one cell, and it can create protein out of DNA. It's the same code. It's the same logic. Life is so good at it. It's not because it's simple that this ball is small. It's because it's complex. Don't confuse cause and effect. The linear associations are not the simple basis of the code. They are the result of the complexity of the code. And we can see it. And once we start looking at and analyzing this data, we can start making we can notice obvious things. One of the most obvious things is there's start and stop all share the same nucleotide, which is the jack of diamonds, which happens to be the weakest nucleotide. So life said, hey, if we got to have start and stop, let's not waste a strong nucleotide. Let's use the weakest one. So it's the first nucleotide in all the stops, and it's the second nucleotide in the one start. And then the code goes through a rainbow of water hating at start through water neutral to water loving at stop. So it has a spectrum of these properties that we can see in the metadata. But I mean, there's just thousands of observations. So you could say all the clubs love water, all the diamonds hate water. Well, that was easy. I mean, what we're going to do is we're going to give these molecules the names of the variables. So, it's easy to do. Just plot them out, where they fall. Well, glycine falls into this codon, so give it the name. That's the ace of spades. Okay? The two of spades is arginine, the three of spades is tryptophan, and the four of spades, that one's problematic. We could probably talk about that later. But so we can start to say things about the molecules based on their names. How many codons are given to each amino acid? Well, if it's a club, it'll get 2. All clubs get 2. That's a rule. That's hard and fast. Oh my God. If it's a 2, it'll get 6 unless it's a club. Okay? So all the ones that get 6 codons are 2s. Well, 2s are important codons. So anyway, once we start putting the data into a mathematically correct graph, we can start analyzing the data and we can see properties of the data that suggest properties of the code that created it. And they give us identities of molecules and the properties of the molecules. I mean, it's an enormously powerful code. It's the most interesting thing you'll ever see. So if you think it's boring, it's only because you don't know what you're talking about. This is the most powerful code in the universe. This is the most interesting thing on Earth. This is the most important thing in science. Understanding the genetic code is more important than anything else in science. This is what created us, the genetic code. Well, we got to try and get it right. At least we got to try and make an effort. We got to take it seriously. This is a code. It's not a friggin' recipe.